Hello, welcome to video 54 in the lecture Advanced Mathematic Modeling. So in the last videos I showed you how to construct deterministic or random fractals as mathematic objects, and for these perfect fractals we were able to find the self-similarity dimension. So we directly had the formula for the fractal dimension in terms of the way the iteration process, the way the fractals were generated. Now if we go to our object in nature, so we have some coastline, some plant, some whatever, some surface, and we want to obtain the fractal dimension, we need a formula how we can compute this that works in practice. And this is what I'm going to show you in this video. So let's see, let's repeat first the way we defined the fractal dimension so far. And this is usually called the box dimension, or sometimes called the box dimension. And this means, let's say we have here a fractal. That's the object we are interested in. And now we want to obtain the fractal dimension. So we put in here our lattice with a certain scale, and then we see now, so then we have small boxes of smaller scale, and then we see how many boxes are hit. So we want to make a covering of the object. By boxes. So this means we have to count how many boxes we need to cover the whole object, and then we would have this box, this, and then we would have maybe here 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes at these scales. Okay? Then we count number of boxes, at scale epsilon, and we call this n of epsilon, and then we define this box dimension, and we give it here a 0 for a reason we will see later. We call this as the limit epsilon goes to 0 of the log n of epsilon divided by the log of 1 over epsilon. And this is how we defined the dimension in the lectures before. But this is in practice not how our fractal dimensions are obtained. And the reason is that this is just too inefficient here, because like if, in particular, if you have higher dimensions and then you have many empty boxes, so you run in your computer, so you meaning you don't have the same weight in your computation in areas where you have a lot parts of the fractal, in other areas where there's nothing from the fractal. So we in order to be more efficient in the computation, it's desirable to have a measure which directly weights parts where the fractal is more dense. These parts are weighted more strongly. And this is important if there is not enough data. So if we have sparse data, which is very often the case, and we cannot look at this for many orders of different scales, so we need a very efficient algorithm, otherwise also our estimate of the dimension is not so good. And so in order to introduce the better techniques, let's say we want to measure the fractal dimension of a cloud of points. cloud of points. So again we have here our lattice of boxes. So this is as before, and now actually they should be all equal size, so these are a bit too small, but okay, imagine this would have all the same size. And now we have a cloud of points somewhere in here. So that's our fractal. And now I want to have so we can count now the number of points in the cloud which are in box I. So and then have Ni, this is the number of points in box I. And then of course we can now do the same thing before, but this is of course, this capital N is a different than this here. So that's here, that's just the number of points. Maybe I should have give this a small n, that we don't that we see that's a different thing. Yeah. And then of course we can now calculate also the number of boxes I need to cover the whole thing. But I can also introduce a probability Pi. So that's the Ni divided by the total number of points. Yeah. So that's then the probability that a point of my cloud of points, that a point is in box I. Probability of a point to be in box I. And now we want to calculate the fractal dimensions of our cloud in terms of these Pi here. And maybe I directly write you the formula now how to calculate such a dimension from this Pi, and then discuss later what this formula means. Yeah? So now we can define a generalized dimension. Generalized fractal dimension. And for this first first let's say we write down some kind of information measure or some kind of entropy, and we call this here information of order Q, which depends on a certain scale epsilon. And Q is a number, it's a parameter. And we define this as 1 minus Q times ln the sum of a logarithm of the sum of this Pi to Q, and we have to sum over all boxes. Yeah? So that's the definition. And so we take our probabilities in all boxes, we take them to power Q, sum this up, take a logarithm, and divide by 1 minus Q. And this is called the Renyi-information. So this is an object which was defined in statistical physics to calculate a generalized information content in such a distribution. And now from this we define now our generalized dimension. So the dimension of order Q, we define it as the limes epsilon goes to 0 of our Renyi information Q, which depends on our scale epsilon, divided by the logarithm of 1 over epsilon. And so it means now we have infinite many fractal dimensions, and this is the generalized dimension of order Q. Okay, now and when I now introduce it like this, so it comes out of the blue, and then most of you will say, so why this, and what can I understand this? Does this make any sense? And this actually was derived by Henschel and Procaccia. In 83, so some years after Feigenbaum. So at this point when people were interested a lot to calculate fractal dimensions and looked for efficient algorithms, and in particular there was the idea to give more weight into more densely populated areas in such a fractal. That's why the point was to then introduce such here probability density, and then we have a probability density. Now we have a measure of a probability density, and then people could just zap in or take into account concepts which were existing in statistical physics, and one was this Renyi-information. And so, but what this means, let's see what happens if we take Q equals to 0 here. Just to get a feel of this. So we want to calculate the fractal dimension d0. So we take the limits, epsilon goes to 0, so our boxes go to smaller and smaller. So, and then we need now the Renyi-information of I0, but if Q is 0, all the probabilities are taken to power 0, so we just have here ones. So and 1 minus 0 is also 1, and then we obtain just the logarithm of a sum over all boxes I divided by the logarithm of 1 over epsilon. But you have to see, now we take when we take this exponent p to 0, now, and we had this before, it depends if this p is larger or smaller. If we have 0 to 0, we have 1. If we have something not 0 to 0, we have if we take 0 to 0, we have 0, and something not equal 0 to power 0, we have 1. So we sum here only over all boxes which in the coverage. So we sum only over these boxes which really cover. Yeah. So this means actually we have here the limits epsilon goes to 0 from ln, the number of the boxes we need divided by the logarithm of 1 over epsilon. And this is exactly the measure we had here before. Yeah? So you see, if we take here the value q equals 0, the way we treat a number to power 0 and we sum over all boxes leaves us exactly to the number of boxes we need to cover our fractal. So this q equals 0 is exactly our box dimension d0, and that's why we gave this here the number d0. Now one can now take other orders of q, and if you see, if you take higher orders of q, we give more weight to these areas where this density is higher. So that's automatically, by this way we can weight this more high. And one case which is taken often is q equals, or taken sometimes is q equal 1. But q equal 1 is a bit weird here in this sense, because if you take q equal 1, we divide here by 1 over 0, yeah, and but then we take the logarithm of p to power 0, the sum of all p equals to 1, yeah, and the logarithm of 1 is also 0. So actually we have here, if we take q equal 1, we have 0 divided by 0. So we have something which is not really defined, but we can look what is the limes if q goes to 1 of our Renyi-information. And now we can take the L'Hopital rule. So we take the limes q goes to 1, and so we take the derivatives of this fraction. So we take d over dq of this here, of logarithm, the sum pi to power q, divided by d over dq of 1 minus q is minus 1. So what we use here is the L'Hopital rule. Where do I write this? Maybe I write this here. And I hope you know this rule, how you can derive a limes if you have a fraction of 0 divided by 0. So we have now to calculate this here, and now we have to calculate here the derivative of this here. So this equals, so let's see, so we take maybe write it a little bit deeper here. The limes q goes to 1, so now we take the derivative. So first we take the minus sign, so we take the minus sign here. So and then we take the derivative of the log. So this is 1 over the argument. So then we have here the sum of this pi to power of q, and then we take the derivative of the inner term, and we take the sum of, now we take d to dq of pi to power q, and this whole with the sign minus 1. Now we have to calculate this derivative. Let's do this. So side calculation, take the derivative d to dq from p to power q, and so we do this by rewriting this p to q as e to ln p times q. Now we can take the derivative to q, so this is ln p times p to q, and this is what we needed here. And now we can continue our calculation of this limes here, and we see, maybe I can write it directly here. If we plug this in here, then we see this is, so there you see, now we can take the limes q to 1, so we have here the sum of pi to power q, this equals 1, and here we have this ln p to q, this q we can take again 1, and then we end up as with minus pi times ln pi. And so this is our Renyi entropy of first order, Renyi-information. And you see this is just and you see this is just the normal entropy here. So if you know, entropy is a measure of information, and so this Renyi-information is just a generalization of the normal entropy. So p times the logarithm of p, yeah, and then sum over all boxes and the minus sign. Yeah? So actually, if we take this limes of this here for q equal, if you take q equal 1, we have to, this is at first glance not defined, but if you take L'Hopital rule and look carefully, we see this exactly goes to a normal entropy. And then, now we can see that we have the fractal dimension. That's now the limes of I1 divided by ln of 1 over epsilon. So this is minus the limes epsilon goes to 0 from our entropy pi ln pi divided by ln 1 over epsilon. And so now we have a new way to measure a fractal dimension. And this is we get this by calculating the information content, so the entropy in the distribution of our cloud of points, and see how does this entropy scale with our distance of the size of such boxes, and the scaling of this information content with the size. This gives us this d1, the information dimension. But in practice, even more important is the case when q is not 1, but q is equals to 2. And this is the correlation dimension. And this is really maybe the most common used way to compute the fractal dimension. And so we take the case q equals to 2. And then we obtain the fractal dimension of order 2. That's the limes epsilon goes to 0. And then we take a log of the sum of our pi squared. Look at this here, so we take the log of pi squared, and then we have here by 1 minus 2 we have a negative sign, and this negative sign, when we plug this here, is that we can, instead of taking logarithm of 1 over epsilon, we can take logarithm of epsilon. So we just divide by logarithm of epsilon. And so sometimes this is written as the limes epsilon goes to 0 from the log of here a correlation sum of epsilon divided by log of epsilon, and this correlation sum is just the sum of this pi squared over all boxes I until n of epsilon. Of course, we need only to sum over the boxes of our covering, because for the other boxes we have 0 anyhow. So that's then the definition of the correlation dimension. And why correlation? How can we interpret this? C of epsilon, that's the probability that we have 2 points to have 2 points of the fractal in the same box. Because here we sum this probability squared, yeah? So it has something to do with a correlation, yeah? Because we have here again an expectation value or sum of pi squared, yeah? That's why it's called the correlation dimension. And now the cool thing is, in order to compute this, there's a cool trick, and that's the famous Grasberger-Procaccia algorithm. And maybe to introduce these people a bit, Grasberger, that's a German statistical physicist, and Procaccia, statistical physicist from Israel. And at this time there were people, when they would develop this, people were eager to calculate fractal dimensions of chaotic systems, of strange attractors, and they started to look for fractal in all kinds of objects. And then these two guys came up with this correlation dimension and found a very cool way to calculate this probability. And so the idea is, so the computation in practice, when we say this correlation, now they typically call this epsilon r like a radius. Let's keep it now the notation they used. So that's the probability that that 2 points on the fractal have a distance xi minus xj, these are the 2 points, have a distance smaller than r. And then they say, okay, we calculate now our correlation sum as 1 over n squared, so the number of points squared. Now we sum over all pairs of points. We take here the Heaviside function of the distance of our scale r minus the distance of 2 points xi, xj, and this is the Heaviside function, so theta from s equals 1 or 0, depending if s is larger than 0 or if s is smaller than or smaller equals 0. That's the Heaviside function. So we measure only here these pairs of points which have a distance which is smaller than the radius. So in practice now, we need to calculate our next neighbor search. And so there's algorithms for this. So if we have now a cloud of points in the fractal, and let's say here we have a specific point, that's our point I, Now we make a radius of r around the point, and then we need to count how many next neighbors in the fractal are there which have a distance smaller than r to our specific point. And that's something which can be calculated rather efficiently compared to other measures to calculate fractal dimensions. So that's then the correlation sum. And now how is this done in practice? I mean, we still would need to make here this leanness r, this radius goes to 0, which is hard to do. But so that means in practice we do again a log double logarithmic plot. Then we say we get our d2, so obtain d2 as the slope of a double logarithmic plot of our correlation sum versus r. So this is how this is done. So what we do, we make here a plot. Here we take the logarithm of our sizes. Here we take the logarithm of the correlation sum, and this is now something which is increasing, because the larger the distance, the larger the ball in like I mean, you can in principle, the fractal can be in a higher dimensional space, and then this whole fractal dimension to calculate this gets computational really demanding, and then you need to find the number of points and balls in this higher dimensional space with the radius r, and this number of points increases with the size. So here we have something which increases, and then we take now equally spaced radiuses on a double logarithmic scale, and have this such a plot, and then you look for the scaling regime, and the slope here gives you the fractal dimension d2. And so like you do a next neighbor search in a high dimensional space for different scales of the size of this circle or a volume or whatever. And this is the way in practice one can obtain the correlation dimension. And so this algorithm is one of the working horses, and it's one of the best used or best algorithm in practice to calculate fractal dimensions. Of course, there's many variants and more efficient algorithms if you tune this a little bit more, but this should give you the idea. And and here I hope it was not too confusing, so I showed you how this is really done in practice, like the real thing, like how this generalized dimensions are calculated. And these DQs are not only now a calculation trick, but like if you calculate now the fractal, so first, I mean, you see the fractal dimension is also not really well defined. There's many definitions of a fractal dimension, and depends what you look at in the system. And in particular, when we go to higher orders Q, we weight areas with higher density more strong, and so we obtain different functions, so different values of this dq. In general, the larger this q, the smaller the fractal dimension. So in general, if we have here this q, if it's 0, 1, 2, and so on and so forth, and we have here the fractal dimension dq, this is our decaying function. Yeah, so maybe it will look like this. So the higher q, the smaller the value of our dimension. and this gives now a way to obtain more properties of our fractal if we see how, if we find some systematic way how the generalized dimension decays with Q. If we know this curve, we get more informations in the multifractal structure of the fractal, but this goes now beyond this what I want to show in this lecture. So I hope I gave you some introduction. What are fractals? So how properties of a system can change with scale, and then we saw this. We started in the measurement of objects, and what is dimension, and but you see now, if we now look how does the information content scale with the size, how does a correlation scale with size, we obtain different kind of fractal dimensions. And in the end, what we do, we just look again at power law distributions, and what we do, we describe the geometry of our objects by such power laws if we want to see how systematically some properties change with scales. Yeah? So the fractal dimensions are intimately related to the objects of this lecture. So the course is starting to come to an end, even though the material, the topics get even more and more interesting, and I have to make a selection. But maybe to follow up this idea, in the next videos we want to look more systematically what does it mean if we scale, if we look at systems at different scales. But for the moment, thank you.